In this video, we will be finishing stamp number 5, and we will be going over 29, 33, 34, and 46. Alright, starting with 29. A full swimming pool has 67,000 gallons. When it begins leaking at a continuous rate of 7% per hour. How many gallons of water will be remaining in the pool after 5 hours? Round your answer to the nearest whole number of gallons. At what time t will the pool be half full? Round your answer to three places after the decimal point. Alright, so full swimming pool has initial value of 7,600. All right, it begins leaking, which means it is decreasing. All right, and it's decreasing in the amount of water in the pool. All right, and so when it's decreasing, we go A is equal to P times 1 minus R, being the rate to the T. All right, it's the only decrease formula we use. All right, so we have 7,600 times 1 minus our rate at which it's decreasing. All right, that's 7%, 0.07 T. All right, that will give us a formula of how much we will have remaining at a given time in hours. All right, so T is hours. All right, part A for this problem asked about the amount of water in the pool after 5 hours. All right, so after we have the formula, we go 7,600 times, well, I can change this to 0.93 to the 5th. All right, and so for problem 29, 29A, all right, our answer is all right, so that answer is 5,287, and it says round your answer to the nearest whole number, so that would be your answer. Now, that answer is different from the answer on the semester exam review answer sheet on the MCPS website, so be careful with that answer. That they gave a 10,000 answer, and this isn't increasing, but it's decreasing, so be careful with that. All right, part B asks what time, so you're asking about a time. All right, will the pool be half full? Now, two ways of doing that. You can figure out what's half of 7,600, which is the way we're going to do it. I'm going to say 3,800. All right, 38. When is this situation? When is the time? 9,3 to the 5th. When is this? Oops, sorry, not 5th, but T. All right, when is that time going to be equal to half? Or when will the pool, the amount of water in the pool will be half of where we began? All right, this situation. So, setting that equal to 3,800, we divide both sides by 7,600. All right, that will give us 1/2. It's equal to 0.93 to the T. 0.93 to the T. All right, and from here, we're trying to get T by itself. So here we go, logging again. All right, we're going to do our log base 0.93 for both sides. And remember, you can do this in a calculator if you would like. I hope it's a calculator problem. This works every time. All right, what will happen to this? Delete it. All right, T is going to be equal to log 1/2 or 0.5 over log 0.93 using the change of base formula. All right, and that's going to give us, let's check that answer, log, I'm going to go log 0.5, close my parentheses, divided by log 0.93, close my parentheses, and it says that it's going to take 9 point, and we're rounding to 3 decimal places, 551 hours. All right, number 33. A golfer hits a ball from the ground at a 20-degree angle to the horizontal with an initial velocity of 132 feet per second. A, get the equations. B, find the location after 2 seconds. And C, when will it hit, how far will it be when it hits the ground? Give your answer correct to 3 decimal places after the decimal point. All right, so first thing we need are these equations from the review, the formula sheet. All right, so we got a lot of calculator work to do here. All right, first things first, let's get these equations. All right, you got x is equal to the initial velocity cosine theta. All right, so these formulas will be given to you. T and y is equal to negative 16t squared, all right, plus the initial velocity sine theta times t plus initial height. All right, so slide those out the way. Let's see if we can get the equations. All right, x is equal to, this is part A, x is equal to, our initial velocity for the problem is at 132 feet per second, cosine 20 degrees t. All right, y is equal to negative 16t squared, which is half of acceleration due to gravity, t squared, plus 132 sine theta t, all right, plus 0, all right, because the ball is being hit off the ground. All right, got that done. That's A. All right, now let's get all this stuff in the calculator. All right, takes us a little bit if we remember some of the things that we did in the calculator. All right, so first things first, let's change our mode to, we're going to change to degrees. We're dealing in degrees. We're going to change from function mode to parametric mode. All right, so changing that first. All right, I'm going to put the equations in. You notice we get the x sub 1t, y sub 1t. All right, typing our equations in, 132 cosine 20, which would be in degrees since our we changed the mode from radians to degrees. All right, and our y component is negative 16t squared plus 132 sine 20 close t. All right, now if we hit graph right now, we're not going to get much of anything. All right, not going to give us anything. So we need to change our window a little bit. All right, golf. All right, you hit the ball. All right, our T min, we're going to change. We usually just change our T max to 6. It was at 2 pi. All right, and in our class, we usually change this to 0.0. I think 0.05 is what we would change it to. Give us a good idea of what's going on. All right, x min. All right, we want to go from start, which is 0. All right, and we need it to stretch out. I'm going to say like 450. All right, might be wrong, but we'll take a look at it. We're going to go by 50s. All right, y min, well, 0 is the ground. I want to see the ground. All right, y max, let's say 50. Might be off a little bit. We'll know. We'll see in a second. Actually, let's make it 100 and see what happens. All right, and we'll let this go by 5s, I guess, 10s, I don't know, 5s. All right, so let's see what our graph looks like. All right, it goes up. Hey, we can see it. We can see what's going on. All right, if we want to make it a little better, we can. Let's take this and make this 400. All right, that takes off a little bit of the stuff that was over here. All right, take a look at it real quick. All right, and then we want to go back and we want it to be a little bit wider. It's up to longer. That's up to you. We can take away some of the Y max. Let's make it 50. All right, so there's the path of your golf ball. Now, you notice that, well, we went by 50s, so that's 50, 100, 150, 200, 250, let's see, 100, 200, 300, about 350 looks like it lands somewhere near 350. All right, not sure. They want us to give a better answer than what I just gave you. So let's see. All right, so step B says, give the location of the ball after 2 seconds. And there are a couple of different ways. All right, before we could just hit, second calc. Oh, we can, second calc value. All right, and type in the time we want. Well, we want 2 seconds. All right, that'll give us, it'll scroll, instead of us tracing, it'll put us right there. All right, and so A, we have here. B, all right, B, the answer is, we are 248 feet, 48 feet, 3 decimal places, so 0.079 feet away, and 26.293 feet high. At 2 seconds. That would answer our question. All right. All right, C. C takes some work. C will take some work. All right, the various ways we can do this. All right, before in our class, we kind of fudged these problems a little bit. We didn't get exact with it, but I'm gonna try to get exact with it today. All right, it says, how far is the ball from the golfer when it hits the ground? So what is its height when it hits the ground? The height is, all right, which is our Y. We're saying that Y is equal to 0. All right, and if we do that, if we think about it for a second and think about our path, all right, the Y would be 0 at the beginning and the Y would be 0 at the end. All right, so let's see, what can we do? We can set this whole thing to 0. So we go 0 is equal to 16t squared plus the, 132 sine 20t. All right, so what we're trying to do right now is find the time, find out when it hits the ground. All right, and we can solve this. Both of these have a t in it. We can factor a t out. 0 is equal to t times 16t plus 132 sine 20. All right, and what happens here is that one of them, t is equal to 0, is when it, right before it struck, right before the golf ball struck, and then 16t plus 132 sine 20 is equal to 0 also. So we're doing 0 product rule. This is when the ball hits the ground. All right, how far is the ball from the golfer when it hits the ground? So there you go, right there. So if I think we're missing something, it should be a negative here. Sorry, negative. Okay. All right, now if we solve for this, let's say I subtract this from both sides, 132 sine 20, or let's just say I move it to the other side. When I move it to the other side, it changes signs. So that's negative 16t is equal to negative 132 sine 20. All right, and then I'm going to divide both sides by negative 16. All right, and it tells me my time it hits the ground. All right, so we're going to get as many decimals as we possibly can for this problem. We want a pretty exact answer. If we could use this and plug this back in, and it would give us an exact answer. So let's write that first. All right, so we're going to say 132 sine 20 degrees all over negative 16. Oops, I'm sorry. Negatives are gone. 132. All right, that's our exact answer for the time. Let's see what that time is. 132 sine 20, close parentheses, divided by 16. All right, and that gives us a time of 2.821666182. All right. All right, that's the time it hits the ground, seconds. All right, now we could use either one of these, but now that we know the time, we can find out how far by plugging this answer back into the x coordinate, the x equation in your parametric. So we could take this. All right, and this will give us how far the ball is away. All right, that's our x distance. So we could go x is equal to 132. I'm going to just draw a little line so we know where we're working here. 132 x is equal to 132 cosine 20 times 132 sine 20, all over 16. And let's see what we get. All right, I know that's not the way we did it before, and we didn't get an exact answer before, but this should give us an exact answer if we do it correctly. Let's see. All right, so I already had, well, let's just type it all over. All right, I don't know if you can see it, but we're going to type it in. All right. So 132 cosine 20 times 132 sine 20 divided by 16. All right. All right, and that gives us a value of, I don't know if we can see it. All right, gives us a value of 349.9978. All right, if we type all that in. All right, let's write that. 349.99, all right, and that is feet away. All right, and so when we do that, just make sure that we put all that in parentheses, and that should give us the answer. And there's number 34. The punter kicks a football from an initial height of 2 feet with an initial velocity of 82 feet per second at an angle of 63 degrees with the horizontal. All right, so right away, let's take that important information. We got 2 feet, all right, off the ground. All right, that's going to be your initial height, all right, with an initial velocity of 82 feet per second, all right, at an angle theta of 63 degrees. All right, all the information we need. All right, write a parametric equation that fits that situation. All right, so A, pen's getting bad. A is going to be 82 cosine 63 degrees T. All right, and that's for X. All right, your y is negative 16t squared plus 82 sine 63t plus 2. All right, so there's part A. Now let's spend some time getting the equations in. I'm just going to clear this. All right, we go. Sometimes it's easier to clear. All right, we're just going to clear the equations from the last problem. All right, 82 cosine 63 close t and negative 16t squared plus 82 sine 63 t plus 2. Alright, so I wrote that wrong. Parentheses t plus 2. Alright, all in. Alright, I'm going to my window and I'm going to see if I can't change this around a little bit as a football. I'm going to lower this. I'm not sure. I'm just going to make it what's in feet. So let's say 350 would be plenty. All right, it is football, so you would hope that it would be less than 300 feet, so give or take. All right, 0, 50, I'm going to keep all that the same from the last problem. All right, so if I hit graph, let's see what happens. The ball went up high and it fell. You see that graph? So we need to change it around a little bit. We need more y. We need less x. More y and less x. So less x would go, let's say, I want to take, I guess we can go to 200 feet. All right, by 50s or 25s. All right, and then your y. Well, y max is at 50 right now. Let's make it 100 feet in the air. And let's see what happens to our graph. And that is much better. All right, just a couple of minor changes. So some people are gonna say, well, what's the window? All right, and so there's your window, 0 to 6 by 0.5, 0, 200 by 25, and 0 to 100 by 5. And you can always pause and go back and try to figure out how we did this. So always pause and go back if you need to. All right, so we got that graph. Now let's answer the questions. This is, what is the position of the ball at 1.5 seconds? So I go to second trace or second calc. All right, I can type in 1.5, enter, and it tells us where the ball is. All right, where the ball is at 1.5 seconds. If you look closely, all right, it has all that information there. You can pause it right now if you want to write that answer. All right, I still got to write the answer. So when t is equal to 1.5, we're at 55.841 away in the x direction away, and 75.594 in the air. All right, there's B done. All right, C, it says a player 6 feet tall. Now a player 6 feet tall is standing 50 yards away, 150 feet. All right, so C, player is 6 feet tall. All right, standing 150 feet away. 150 feet away. All right, from the punter, directly in the path of the kick. Will the ball go over his head? So if we can think about this situation that we're dealing with, all right, the ball gets punted somewhere 150 feet away. There's someone standing there 6 feet tall. We want to know, will it go over his head? So if we're looking at our graph, and this becomes a graph situation, let's say graph for a second. When we look at our notches at the bottom, we can kind of try to guess this. Now, what were our notches for this problem? Window. Our notches in the x, or our x scale, was 25. This is how we can make an educated guess before we find the exact answer. 25, 50, 75, 100, 25, 125, 150. All right, that's where 150 is on our graph. All right, and so we're trying to figure out whether or not that soccer player standing there is going to hit 60. So if we trace, we could trace, all right, and scroll. All right, as we continue to scroll, all right, we're looking for X being about 150 or a little bit past. All right, and so we could say right there at 150 feet away, that's that X value. Y is 35 feet in the air. All right, that's a little bit over 150 feet. So the answer to the question is yes, the ball will go over the soccer player's head. It definitely will go over his head. All right. Now it says justify your answer. All right. Now this is where it gets tricky for you guys. All right. For us, we could give this value, this value right here, and we could say by calculator, the time at time 4.05 seconds, the ball was 150.770 feet in the air, 35.463 feet high. All right, so it was 150 feet away, I'm sorry, and 35 feet high. All right, therefore the ball will go over. And I know some people are going to write this better than I am writing it right now, but therefore the ball will go over his head. All right. All right. Now, what's the last part? We have D. I'm getting shadows on my board now. Sorry. All right. D. Let's see. D says, suppose that the ball hits the ground. When will the ball hit the ground, and how far from the punter will the ball hit the ground? So this is a lot like the last problem we did in problem number 33. Remember, we're doing 34 now for those who didn't recognize. All right, 34. All right. So once again, let's do this problem. We want to first for the way we're going to do this. One, we want to set your y equation to 0. Set the y equation to 0. All right, so we can find the proper time. All right. Step 2 is to take that, plug the time. All right, into the x equation. All right, and like I said, that's a little bit different than when we did it during the year, but this is more exact, and we're on video now, so I can't put out half answers. All right, so suppose the ball hits the ground. Let's figure this out. All right, in this case, number 46. A pilot sets his plane to travel due west at 400 miles per hour. A wind is blowing toward the northwest at 60 miles per hour that blows the plane off course. A, what is the ground speed of the plane correct to 3 decimal places? B, in which direction is the plane traveling correct to 3 decimal places? So 400 to 600, it says almost times 7. All right, and so we take a plane, we can kind of draw our vectors. All right, let's say I make that the plane vector. All right, and we're saying that that's 400 due west. All right, so we're looking for a plane vector. All right, and our plane vector is going to be negative 400, comma 0. all right? Then we have a wind vector that's blowing toward the northwest, all right, toward the northwest. All right, all right, first of all, we should know what northwest, north, east, south, and west, and I know there's a mnemonic for it, I just don't know what it is. All right, just made sense that we live on the East Coast. All right, this is Silver Spring, Maryland. All right, LA is in the west. California, West Coast, Pacific. All right, so let's make a smaller wind vector going diagonally up and to the left. Smaller vector. All right, I'm gonna knock some of it off, and this would be my wind vector. All right, this is my, this would be my displacement vector. All right, so this would be plane vector, this would be my wind vector, and this would be plane plus wind. All right, and so that's what we're looking for. All right, so my wind vector. All right, in this case, we take our speed, which is 600, cosine the angle. All right, and so we're going 135, all right, comma 60 sine 135 degrees. All right, and that would be my wind vector. Let's simplify that. All right, so we got 60 up. Let's make sure that we are in degrees before we start this problem. We're in degrees. All right, and so we go 60 cosine 135, close it. All right, it gives us negative 42.426. All right, and then we can go second enter and just go back and change your cosine to sine. Change the cosine to sine. All right, should be something similar but positive, yes. And that's 42.426. All right, so we have a plane vector and a wind vector. All right, now from there we want to add the two vectors. The plane vector plus the wind vector. All right, if we add them, we should get negative 442.426 and 42.426. All right, hopefully there's no calculator needed for those. All right, we're just adding those two vectors. Now, that is this vector, all right, and it should make sense that it goes a little bit more to the negative and then it goes up. All right, now from here they're asking us for ground speed, and so the ground speed is the magnitude. All right, just remember ground speed, we're looking for magnitude. All right, and so the magnitude is going to be the square root of all of this stuff, parentheses negative 442.426 all square plus parentheses 42.426 all square. All right, and that's going to give us our ground speed. Let's type that in carefully. All right, second square root, parentheses negative, and we really don't need the negative, but okay, whatever. 426, close it, square it, plus, close it, 42.426 square. All right. And so we end up with 444.456, all right, miles per hour. All right, so A done. A is done. All right, now the next question says, in which direction is the plane traveling? Correct to 3 decimal places. And remember our little chart, and like I said, I don't know how many people use it, but we use it. All right, and it works for us until we get them wrong, I guess we're going to keep on using it. 1, 2, 3, quadrant 3, 1, 2, 3, 4, quadrant 4. We say, here we say theta is theta. Here we say theta plus 360. All right, here we say theta plus 180. And here we say theta plus 180. All right, and so we're using, now, looking at the picture, all right, let's look at, that's why we sketch, all right. We are in which quadrant? Second quadrant, guys. All right, so whatever theta we get, we're gonna add 180 to it, all right. So we're gonna say theta is going to be equal to, well, the direction, excuse me, is going to be equal to, and we have to remember our formula, or actually you don't have to remember anything because it's in the formula sheet. We need, for this, we need theta is equal to inverse tan. All right, this allows us to use this, y over x. And so in this case, this is our y and this is our x. All right, so we want to go that the direction is equal to inverse tan of 42.426 over negative 42.426. All right, plus 180 degrees, and that'll give us the answer. Now, some people will say north of west and all of that. All right, and so that's fine also, but this gives you the direction. It gives you the direction. All right, so let's see if we do that right. Clear. Let me speed this up, hopefully. 42.426 divided by negative 442.426. Close it. All right, that gave us negative 5.478 plus 180. All right, will give us the direction we usually get. All right, 180 degrees, and that's 174.522 degrees. All right. Now, in the textbook, I'm sorry, in the exam review answer key, they give you an answer of 5.478 degrees north of west. All right, and that's one way of writing it. And if you think of it, they're saying that if you were west and you go towards the north 5.478 degrees, that's where you would be. And that's exactly where you would be. All right, so either answer is acceptable. All right, and thank you.